Hello and welcome to our presentation on characteristic mode analysis of mutual coupling. The paper is recently accepted in IEEE transactions on antennas and propagation. I am Dr. Ghosal. The brief outline of the presentation is given here. So why mutual coupling is so important in antenna array? So if we anticipate one antenna, it induces some parasitically coupled current in the next antenna. So the coupling between two antennas have been characterized in terms of this coupled current here. If we go by the method of moment technique, the coupled current can be written like this, which is dependent on the excitation on the first antenna. So without information of this first antenna, we can actually predict the coupled current modes using conventional TCM like this. But it has the complexity order of U cube n cube per U number of antennas. But if we go for the theory of coupled characteristic mode TCCM, it provides the solution using order of n cube problem. So what is TCCM? TCCM provides the coupled modes as a linear combination of these isolated modes like this. The first order solution of TCCM provides a closed form solution, and if you see that this closed form solution matching quite well with the method of moment techniques here for a pair of dipoles here. So with only the first pair of odd and even modes, the results are matching for the coupled current. Similarly, the coefficients, modal coefficients is matching with the coupled current as well as the source current here. And the mutual interactive power independent of excitation is also shown here. Next topic is current correlation coefficient. Unlike the field dependent ECC, we are providing the current based correlation coefficient like this way, which is quite well matching with the measurement technique here. And the comparison with the full wave solver antenna toolbox, we have shown the port parameter variation here, which is also well matched with the solvers. The next thing is the physical interpretation of substructure modes with respect to the TCCM. We show that the substructure eigenvectors are actually equal to the coupled eigenvectors, that is the isolated mode, if we compare these two equations. But the coefficients of the eigenvalue, that is a little bit different from the isolated eigenvalues, that difference represents the coupling amount. For comparison, two pairs of circular plates are shown here. The idea have been later used for the ground coupling analysis. So based on this combination of this idea, we can control the coupling between the ground plane and the upper patches here. And the comparison for the first pair of modes are shown here. In the next, we have provided a safe synthesis technique for decoupling structure between two antennas. We are putting a parasitic structure to control reduce the coupling between these two antennas. So the coupled current for this element is shown here. If we see for different length ratio of this structure, we can show that there are substructure modes in A and B are shown here, that is odd and even modes. So based on this length, the amount of coupled current is actually reducing for this LR equals to 0.5, that is the length ratio. And with that length ratio, we can see the maximum coupled current is also reducing. From comparison with the port parameter, we see that with 0.5 C, the coupling is minimum. A comparison with the antenna toolbox is provided here. We can see also the field perturbation with this 0.5 lambda C is also reduced here. And the general design procedure is shown here. The brief outline is shown here. Thank you so much.